A half-life is just one specific type of exponential decay, and it uses the same formula that we learned about, where A is the initial amount. In this case, it will be our sample size. B is the growth factor, and X is time. Sometimes you'll see it listed as T. So if we're looking at specifically half-life problems, this is going to kind of be our setup that we see down here. And again, our variables will match. A is still the starting amount, the initial amount. It's the size of your initial sample. B is the growth factor, but because this is exponential decay, we know it's going to be less than 1. And because we're taking half each time, the amount is dropping by half, this will always be 1/2 or 0.5. B will be 1/2 or 0.5 always. Now, the time part is broken up a little bit differently. The bottom is going to, the denominator is your actual half-life time. If something has a half-life of 15 years, you would put a 15 down here. If something has a half-life of 1,000 years, you would put 1,000 down there. And X is very important. It's how much time has passed in the given problem. So most of the time, you're going to have the X left blank, and then they're going to ask you how much time has passed. If 50 years go by, how much is left? If 1,000 years go by, how much is left? So this X on the top is not the half-life. It is how much time has passed in your problem. So about how long will it take for our 1,000-gram sample to be essentially gone? Well, if the half-life is 69 years, and we want to know how much is going to be left after 500 years, technically we would want to know how many 69s go into 500. So I'm just going to say that 69 years is about 70 years. And I need to know, well, what's 500 divided by 70? And I'm going to get rid of our zeros. And I know that 7 goes into 50 a little bit more than 7 times. So it's going to take at least 8 iterations of this to kind of bring this 1,000-gram sample down. So let's kind of see how it plays out. After 69 years, we will have 500 grams, and that's in the first part of the half-life. The second 69 years would leave us with 250 grams. So what's happening essentially is after the first half-life round, half of your amount is gone. So that's all gone and a big chunk left, but then you still have this whole other half. Well, after another 69 years, then we would have a quarter of the sample. And after another 69 years, we're now at 125 grams. And so on. After the fourth cycle, you would have 62.5. After the fifth sample, we'd have 31.25. And now our decimals start to get a little bit crazy. The next will give us 15.625. And then half of 15 is about 7.5, so we're going to get 7.8125. And now we're going to have a lot of decimals. So when we take half of this, I'm going to say we have about 3.5-ish. Really, it's almost closer to 4. And after that, you would have close to 2, like 1 point something grams left from this initial 1,000-gram sample. So you can see that as you take half, you're still going to have a little residue left over. But that's a lot of work. So with a push of a few buttons, we can do this in a matter of seconds. So rather than count this all out this way, we're going to go back to our little half-life formula. We're going to identify what are the important parts. So what's the initial amount? Well, we said we started with 1,000 grams. So we're going to go and we're going to put 1,000 grams in this little spot for A. And I'm not really going to have room, so I'm going to scooch the whole thing over and say y is equal to 1,000 times 1/2 to the what? Well, let's fill in what we know. You know that the half-life is 69. That is super important. We need to put that here. And we're going to get 69. And now this is our general function. We can answer any question that we want using this function for problems like this. But we specifically want to know how much is left after 500 years. So this is where the 500 is going to go. You're going to take this x, get rid of it, and we're going to put 500 in this spot. And just like I did above where I said, oh, how many 70s fit into into 500, you're saying how many 69s fit into it. So this is what you're going to enter into your calculator. Take a second, try entering this, and let's see what you get rounded to the nearest, let's say the nearest 100th. That's 2 decimal places. Well, we get 6.586. If we wanted to round it to the nearest 100th, we would round this up to be 6.59 grams. And that's only a small amount. But if you look, we said that there were between 7 and 8 times that 69 can go into 500. I'm going to double check it right now. Yeah, it goes in 7.24 times. So in between 7 and 8 is where our answer is. And you can see that 6.59 fits right in here. Now I want to show you one more example that's similar to the one that you have on your extra credit. And it does something a little sneaky. So I'm going to scoot all of that up. And it has to do with the time. Okay, this example has a 50 milligram sample. And I'm looking at something that has a half-life of 14.3 days. So we would put 14.3 here. And this is just a problem like any other. But what if they asked you, how much will be left after 5 weeks? Let's write that, after 5 weeks. Well, the half-life is in days. So the units must match. You cannot put a 5 on the top because then you would be saying 5 days. And this is about 5 weeks. So you need to tell me how many days that is. And the number you'd be putting in for X would be 35 days because there's 7 days in a week and you're doing it for 5 weeks. So you would want to make sure that you used matching units. Whoops, not 75, 35. So just make sure when you are trying your extra credit problem or any half-life problems that when you're entering the time that has passed, it matches the same units as the half-life.